Most people assume a self-evolving AI agent actually learns as it operates. The empirical evidence pushes back on that assumption. A research team took an agent, completely froze its underlying large language model, and then froze its memory bank to prevent any new entries. Looking at this benchmark tally for the held-out ALF world evaluation, you can see the result. The frozen system, labeled MemRL, hit a transfer accuracy of 0.479, easily beating the standard RAG baseline at 0.336, and the baseline memory system, MEMP, at 0.421. If the neural network weights are locked and the database accepts 0 new facts, the system mathematically should not be able to adapt to an unseen task. Yet it adapts. This happens because the AI industry currently groups 3 entirely different architectural mechanisms under the single marketing label of self-evolving. To understand what you are actually buying or building, we have to isolate genuine machine learning, where a model's internal parameters update, from stateful memory management, where a model simply searches a growing text database. Diagnosing the exact physical location of what changes inside an agent is the only reliable way to know if an architecture is evolving, or if it is a static reasoner wearing a dynamic context costume. 2 major academic surveys from late 2025 and early 2026 attempted to map the chaos of agent memory systems. The December 2025 survey categorized memory architecture purely by its forms, functions, and dynamics, how a memory is shaped and retrieved. This diagram illustrates the sharper March 2026 taxonomy by Pengfei Du. It redefines agent memory strictly as a write-manage-read loop, containing 5 specific mechanism families. The first 4 boxes represent standard approaches to context engineering and database growth. The agent stores summaries or builds external knowledge graphs to recall later. The 5th family, policy-learned management, is the strict threshold. It dictates how the agent learns how to use the memory it stores. If a vendor's system change lives above the dividing line, you are buying memory growth. If the change lives below that line, you are buying actual learning. Evaluating an AI agent is like auditing an employee. You need to determine if a new piece of knowledge was actually memorized in their brain, scribbled on a sticky note on their desk, or filed away in a Rolodex. This table maps out the 5 strict physical locations, or loci, where change can occur inside an agent's architecture. At the top layer, you have the model weights. Altering these fine-tuned controllers carries a high compute cost and low reversibility, but the knowledge is durable. It survives even if you wipe the agent's memory banks. Contrast the weights against the prompt or core memory blocks. Editing the prompt creates narrow, immediate behavior changes with high reversibility and almost 0 compute cost. The third layer covers external memory contents. This is where an agent stores raw facts, standard operating procedures, and long-term knowledge graphs. The 4th layer is the retrieval and memory management policy. This layer does not hold the text itself. It controls the rules deciding exactly which memories to fetch, update, or delete. Different leading agent frameworks target entirely different rows. LEDA focuses heavily on prompt and core blocks. MemRL targets the retrieval policy. SDAR pushes changes straight into the weights. Because most commercial systems available today only alter prompts and append text to external memory, they remain static reasoners borrowing dynamic context. Imagine a librarian tracking your books, observing which actually make you smarter, then independently reorganizing the shelves to prioritize those high-value texts. That librarian analogy explains exactly how the MemRL framework achieved its high transfer accuracy with a frozen large language model. MemRL stores every new episode strictly as a semantic triplet: the agent's intent, the specific experience, and its historical utility. When facing a new task, the system recalls semantically relevant candidates, but critically, it re-ranks those candidates using a learned Q value. These utility values continuously update via Bellman-style temporal difference learning based on environmental rewards. The LLM doesn't learn. The policy dictating memory reuse does.
The mathematical learning in the policy layer generated an 82% transfer accuracy gain over baselines that lacked memory entirely. MemRel proves that genuine evolution can occur outside the LLM weights, provided the retrieval policy strictly learns from experience. If you give a student a cheat sheet for an exam and then take it away, a collapse in their test score proves they were just reading. They didn't learn the material. Machine learning researchers apply the exact same logic to AI agents. It is known as the memory wipe test. Look at the left side of this split-screen test. A baseline method called Skill-GRPO evaluates on the ALFWorld 3B benchmark. Fully loaded with retrieval skills, it scores an 80.5. Remove those external skills during the inference phase, and the accuracy drops to 60.2, a 20-point loss. The agent relied entirely on the context it was fed. Now look at the right. A technique called SDAR, gated self-distillation with reinforcement learning, requires no external skill cards during inference, yet its score holds up. SDAR uses gated distillation to successfully transfer the underlying operational knowledge directly into the policy's internal parameters. SDAR is a post-training technique, not a live online evolution loop, but it validates that internalizing skill knowledge directly into the weights is technically viable. Surviving the removal of the memory scaffold is the definitive proof that an agent shifted from reading context to possessing internalized knowledge. The AI engineering field is split by a philosophical schism. Two camps are arguing over the exact same architectures, but they use entirely different vocabularies. The memory-first camp includes leaders from Letta, Zepp, and LangChain. They argue that learning in agents is achieved through temporally aware knowledge graphs and highly structured stateful databases. The learning-first camp includes the teams behind MemRL and SDAR. They argue that true evolution requires mathematically changing a controller, a policy, or the core parameters. Both camps successfully build agents that output better answers over time. They disagree strictly on where that improvement physically lives inside the system. To cut through vendor marketing, use this 5-question checklist to evaluate the architecture. First, what exactly changed? What if memory is wiped? What if retrieval is disabled? Does it transfer to held-out tasks? Is the change replayable? Testing performance on entirely held-out tasks and disabling retrieval layers breaks superficial RAG wrappers. It exposes whether the system acquired a generalizable rule or just saved a specific answer. Most commercial systems claiming to be self-evolving fail at least one of these 5 questions. This vertical stack is a 4-layer hierarchy. At the bottom, stored experience grows and becomes structured, where most current systems operate. At the top, memory policy is learned, or parameters internalize the experience. Only these satisfy true machine learning. This architectural debate maps directly to the historical lineage of case-based reasoning systems from past decades. Early case-based reasoning systems also improved their output over time by retrieving past examples, without altering their internal models. Claiming those systems were learning was heavily contested by researchers then. The modern self-evolving agent wave is simply this historical fault line, revived and scaled up by massive context windows. Adding robust external memory enlarges the agent's operational loop, and it yields better performance, but it does not define actual learning. The singular empirical test that definitively separates sophisticated database retrieval from true learning is survival without the scaffold. If this technical breakdown was useful, subscribe to Bearded AI Guy. Drop a comment below with the name of one vendor system you use, and guess which layer of the hierarchy it actually lives in. This entire taxonomy comes from the Human Architect's AI Agents in Action. I highly recommend grabbing the book for the unabridged system map. Tomorrow, we look at multi-agent frameworks, examining whether the new swarm era is just repeating the exact same hype cycle as single-agent wrappers. When the cheat sheet goes away, what does your agent actually know?